Atwood machines are just a special type of compound mass system where you'll have pulleys and things connected by strings. And so they just kind of categorize anything that looks like this as an Atwood machine. Sometimes you'll have them just up and over a pulley like this. You could have multiple masses in here with multiple strings. You might have one on a table and one hanging off a table. But these are really all just versions of compound mass systems. And when you do these types of problems, the overall goal is that we look at the acceleration of the system first, because the whole object, this whole system of mass, accelerates together. So every single thing in there will have the same acceleration. Same thing over on this side. If this 5 kilogram block accelerates down, well, these blocks will accelerate up, and everything has to move as a single unit, and that's what helps get this math solved. So again, I'm going to have you pause it, and so you can jot these couple examples down, and then we'll work them out and solve. In the first problem, when you're trying to identify the system, your system is just going to be comprised of the two blocks, this 2 kilogram block on top, the string itself, and this 3 kilogram block hanging. All of that is my system. Now, things that were left out of that system, other objects that are in the problem, are the earth, the table, and those are external to that system, and so they're going to provide external forces that we can use to understand what's happening to the system. So this 3 kilogram block is getting pulled on with a force of gravity, and that force of gravity would equal m times g, or 3 kilograms times 10 newtons per kilogram, for a total of 30 newtons. So there's 30 newtons of downward force on the system of mass coming from that force of gravity. And the only thing that's resisting that acceleration, trying to pull that system downward, is this frictional force back on the 2 kilogram block. And we know there's friction there because they indicated that with the coefficient of sliding friction of 0.1. If it was frictionless, I wouldn't draw any arrow back, and the only force would be coming from this pulling force. But when you have friction between the block and the surface, then you got to include that. So we'll just solve for that real quick. That force of friction equals mu of sliding times normal force. And they gave me all the values I need. The normal force in this case is just equivalent to the weight of that 2 kilogram block. If the gravity pulls down with 20 newtons, the surface is pushing up with 20 newtons. And so I actually have all the numbers I need, 0.1 times 20 newtons. And so that would equal out to 2 newtons of frictional force back. So this tug of war happening of 30 newtons down on this side of the system minus the 2 newtons opposing gives us 28 newtons total of force trying to accelerate that system. So what I think is helpful is I like to draw what the acceleration is doing at each kind of mass. Just this mass would be accelerating down. This mass is accelerating to the right. And we'll come back to that when we actually solve for the overall acceleration of the system. We write that out as the acceleration of the system is equal to the net force on the system divided by the mass of the system. So we've already determined our net force was the 30 newtons pulling down minus the 2 newtons pulling back. And the overall mass would just be the two put together, which is around 5 kilograms. So I'm going to have 28 over 5, and if I divide that out, that would get me, let me give it just a second and calculate it. 28 divided by 5 gives me an acceleration of our system of 5.6 meters per second squared. So at every single point, that is what the acceleration is. So that block is accelerating down at that rate. This block is accelerating over at that rate. And that's what's common between, that's what ties these together and makes this a system problem, is that we first solve for that acceleration. And then if we want to know what's going on inside of the system, like they usually want to know like what is the tension or how much does one block push on another, then I can just take a single block that's experiencing those forces and solve for that tension. Now, typically you want to pick the block that has the least amount of influences, but if I think about the forces on this block, it has tension to the right. I could get to the tension that way, but it has friction back. Well, this block has weight down and then tension up. So there's really no benefit of picking one over the other. They're going to be equally as challenging to solve. So I'm just going to pick the hanging block to solve for tension, and we'll show what that math would be over here as well for the block on the table, so that we see both sides. So the block that's hanging, let's just take a look at that. It has a downward force of 30 newtons. That's the weight of it. And then it has this upward force of tension that conceptually is not going to be as big as 30. And the reason we know that is because if this block is accelerating down, the downward force would have to be bigger than the up force. When I write a net force equation for that single block, I'd have 30 newtons of downward force minus tension equals that block's mass times its acceleration. And I was given the mass and I know the acceleration, so I technically have everything I need. And I can rearrange that and solve for t. So I'd have 30 newtons minus ma would equal out to t. All I did there is I did a couple steps. I added t to each side, and then I subtracted ma from each side. So that's the two steps there, just kind of combined. But now I'm ready to solve. My mass times acceleration would be 5.6 times 3, which is around 16.8 newtons. So I have 30, oops, let's go back up. 30 newtons minus 16.8 newtons equals tension. So the tension in the rope should equal 30 minus 16.8, which is around 13.2 newtons. So the tension force should be around 13.2. I like to just double check that real quick and work backwards. 30 minus 13.2 is 16.8. If I take that divided by the mass of 3, I get 5.6 meters per second squared again. So you can kind of work the numbers back and make sure that you get out to that acceleration, and that works out. Now, we can go over to the other side and double check that that's correct as well. If we visualize the 2 kilogram block, it would have forces of tension to the right, friction back. It has a weight and a normal. Normal and weight kind of cancel. There's really nothing going on that's interesting there as far as the acceleration is concerned. So I'm more focused on this kind of x direction when I write my net force equations. So the net force on that block is the tension minus the friction should equal mass times acceleration. And when I do that, just if I add friction to the other side, I'll have the tension of this rope should equal mass times acceleration of that block plus the frictional force. Well, I've already solved for the frictional force before, just kind of working that out. I got 2 newtons, and the mass of that being 2 kilograms times the acceleration of 5.6 meters per second squared plus the frictional force of 2 newtons. When I calculate that out, I get 13.2 newtons. So that tension force comes out to the same number whether I solve it using that block on the table or the block that's hanging off the edge. And that's important to realize that the tension is going to be the same in every part of the rope. So it doesn't technically matter which one you start with in order to get yourself to that solution. But it is nice to see it checks out in both, that I'm getting to the same amount of tension force in each. In the second problem, we have two different ropes, tension 2, tension 1. Tension 1 goes up and over the pulley and connects over to this 5 kilogram block. Our plan doesn't change from the previous problem. I have a system of mass. I got this 5 kilogram block that's connected by a string that comes back to the other side, is connected to these two blocks. So my whole system of mass, these tensions are kind of wrapped up inside of the system, and I can't solve for them outright. I'd want to think about this as a whole system moving before I can get to those tensions. So let's go ahead and do that and set that up. The acceleration of our system would equal the net force on the system divided by the mass of the system. What is the net force on the system? Well, I gotta identify these pulling forces of gravity. I have the Earth pulling on this with 50 newtons. That's just the mass times 10. The Earth pulls on this one with 10 newtons, and the Earth pulls on this with 20 newtons. So I have 50 newtons pulling in one direction, and you can think about it as like 30 newtons total pulling back. If I were to re-represent this, sometimes it's helpful to like visualize what's going on. It's if I take this and I straighten it out into a flat line, and I have this 5 kilogram block getting pulled on this way with 50, and it's connected to the 2 and the 1 put together. So this is a total of 3 kilograms. That's total getting pulled on with 30 newtons this way. This combined amount of mass of 8 kilograms, it's having a tug of war on it. This 8 kilogram total system mass is getting pulled on with 50 one way, 30 the other way. And so there's a net force of 20 newtons on this 8 kilograms of mass. That is what's happening for my whole system. I have 50 minus the other two put together. Since they're both working in the same direction, I'm just adding them, 30 newtons. That is all divided by the system mass of 8 kilograms. Add my units in here. And so that's just 20 newtons divided by 8 kilograms. And that acceleration would be 2.5 meters per second squared. So again, draw that acceleration. That acceleration on this side is downward, and that equals 2.5 meters per second squared. On this block, it's upward of that amount. This block is accelerating at 2.5 meters per second squared. Every single thing is accelerating at that rate of 2.5 meters per second squared. So when I go to write these statements of like one force minus the other, I want to kind of reveal what I'm doing, or the reason why I'm always organizing it as, how do I know to write 50 minus 30 and not 30 minus 50? If you get in the habit of always putting the force in the direction of the acceleration first, 50 goes with the acceleration. So any forces that are going with the acceleration come first, minus any forces that are going opposite of the direction. That setup or that logic will always give you a positive number. So then I can just talk about this acceleration as positive, because it's going to be going different directions. On this side it's up, this side it's down, but it's always this value of 2.5. So I just do it as forces in the direction of acceleration minus the forces opposing the direction of the acceleration. Once I have that, I can start looking at the ropes. So it doesn't really matter where I start. I just need to pick an object who has that rope attached to it, So I'm going to pick this 1 kilogram object because it has tension 2 attached to it, and that's going to help me solve for tension 2. So let's draw the free body diagram for the 1 kilogram object. That object has 10 newtons of weight down and tension that will be larger than 10 newtons. And the reason I know it's larger is because that thing is accelerating upward. When I write the net force for that object, it's got tension minus 10 newtons, which equals its mass times acceleration. And I have all that information. The acceleration was 2.5, the mass is 1. So that says tension equals 10 newtons plus 2.5 newtons, or the tension equals 12.5 newtons of upward force. So that means that rope 2, tension 2, has an upward pull on this block of 12.5 newtons. That means that that is also, if this is pulling up at that amount, then that tension is also tugging away from that 2 kilogram block with the same amount. So it wouldn't matter if I used the 2 kilogram or the 1 kilogram to start off with. I chose to use the 1 kilogram block just because I thought that math would be easier. Think of tension, just by the way, think of tension as like you only reference it in terms of, as far as like, how do you know what direction? It looks like it switches direction halfway through. It's because you're always referencing the tension on another object. So the direction is up on this object because that's the way that this object feels that string pulling. This object also feels that same amount of tension, but it feels that tugging downward on it. So these arrows are not conflicting with each other. They're actually saying the same idea. It's just each block feels that pull in a different direction. Just wanted to clarify that. When I look at rope 1, okay, I'm actually just going to move over and look at it at the 5 kilogram block. And this thing had 50 newtons down and a certain amount of tension up that we don't know. It's not going to be the same as what I just solved for T2 because that's a different rope. Tension is the same everywhere along a single rope, but if you have a different rope, that's going to experience its own tension. So that's what I'm trying to solve for now. And when I write out that math, let me shrink things up a little bit. I have the net force is equal to 50 newtons down minus the tension 1 up. How'd I know to write it in that order? Because again, if you write your forces as the force that's in the direction of the acceleration first, that's the 50 newtons, minus the force that's opposite the direction of the acceleration, that'll kind of keep your stuff positive. It's easier to solve for. That should equal that mass times acceleration. And again, solving for T1 then, T1 should equal 50 newtons minus the mass of 5 kilograms times the acceleration of 2.5 meters per second squared. So I just added T1 to the other side, I subtracted MA to the other side, and let's go ahead and solve that out. 5 times 2.5 is 12.5, so 50 minus 12.5 gives you that tension 1 is 37.5 newtons. All right, I like to double check if everything was working out. So I'm going to look at the 2 kilogram block. So if I just solve that is 37.5, then that means that there has to be that same amount of tension 1 of 37.5 pulling up on that. So real quick off to the side, I got apparently 37.5 newtons of upward tension. I had a tension 2 that was downward of, what did we say, 12.5 newtons. And there's an additional downward force on this 2 kilogram block coming from gravity of 20 newtons. So this is force of gravity, this is force of tension 2, this is force of tension 1. So that 2 kilogram block has two different pulling down forces. It has a 20 Newton force pulling down, and it also has that tension in the rope pulling down. So let's figure out what the net force is going on. I got all the ups minus all the downs to figure out the total. And let's see, 37.5 minus 32.5. That gives me a total of 5 newtons of net force. So there's an overall 5 newtons of net force and a mass of 2. Finish that off with the net force equation. Net force over mass should equal the acceleration. Let's try it out. 5 newtons of net force divided by a mass of 2 kilograms equals 2.5 meters per second squared. That's awesome. That works out. So I know that I did my math right. And that would be how you solve a complex mass problem.